Everyone, welcome to another video. Um, this video I'll be solving more Leetcode problems. And okay, we'll get started in a while. How's your week been so far? For me, it's been productive. I'm learning so many things. At the same time, also actively applying for full-time roles and looking for positions in software engineering. And I feel live and just solving lead code problems helps me build consistency and figure out new approaches to solve it. What I realized so far it's not just about solving it once, it's also about consistency on how often you solve a problem. Might also give you new insights or new methods. If you come back and solve it again, it will definitely give you much more inputs. So okay, I'll share my screen and let's get started. Okay, so this is another problem. It's a medium problem called find bottom tree value. So it says given the root of a binary, return the leftmost value in the last row of the tree. For example, if our tree is 2 by 3, the leftmost value in the last row will be 1. What is 1? Similarly, if our tree is 1, 2, 3, 4, there's null here, and 5, 6, and then null, null 7. So the leftmost and the downmost leaf node is 7. So that is why output is 7. So first let's write down what all we know and what does the problem say. Goal is to find the last level of the tree and return the leftmost node's value in that level. Brute force approach. Let's think of the brute force approach first. Can think of the first search DFS. You can DFS the whole tree because DFS attracts depth. So whenever we reach a node deeper than any seen before, we can update the answer. We know DFS goes left before right. So the first node that we see at a new max depth is always the leftmost one. So we can update the answer only when it exceeds the previous max depth. So this can be one brute force approach. Another better approach or optimal approach would be use breadth first search. BFS at the start of each level, we can record the first node we process. That will be leftmost one. We can then keep opening it at each level. When BFS finishes, whatever last record will be the left or deepest node at that level. Another approach could be process each level right to left. That that would be a little tricky for me right now, but one of the cleanest ones. So just gonna go with the optimal approach and try to code it. So from elections, queue, double-ended queue. So we have a definition find left value with root elements and it returns an output integer. So I'm gonna assign a make a variable q and assign the root to it dq d e q u e and result is 0. We need the leftmost value in the last deepest root. BFS level by level. At each level, for the first node, keep overwriting after BFS ends. Last recorded value is the answer, right? So result equal to 0 and then I'm going to do while q. Well, our q exists, we have a root. I'm going to assign another variable called level size and track the level length of the queue. So we're gonna for each level, we're gonna check how many nodes are at this level. Then for I in range, level underscore size, node equal to q dot of left. then I can do if I equal to 0, result to node dot value. So here I equal to 0 means this is the first or leftmost node, this line. And then if I 0, then it's the first leftmost node over right our levels. Right. However, if node left, then q dot apply node dot left. If node dot right, q dot append dot right, and return result. So it should be here. Let's see if this would work if I have an example. So, for example, let's take this one. We'll take this one. Sample. So I have this root. So now, if I'm at level 1, then my nodes are just 1, right? Because in my level 1 is just this one. So this means here my I is equal to 0 and result is also equal to 1. When I go to level 2, my nodes change to 2 and 3. So here I is 0 and I'm returning the last level's leftmost value. So here my leftmost value is 2, right? So it's going to return 2, 3, 4, 6, 4, 5, 6. So I is 0 and my result is 4. And when I move to level 4, just have a single node 7. So now I is 0 and my result is 7. So here my BFS ends and I'm gonna return 7. Now let's think about the time complexity. Um, so we can see every node is visited exactly once. So time complexity so often as every node is visited exactly once. And when it comes to space complexity, each queue holds at least like one level 1, level 2, level 3. So I do where W is height or level height. So So was most fun to learn. The pattern here is BFS level order tracking with overwriting the which level is last in advance. Just keep updated. Leftmost value at each level. Final value is automatically from the best level when BFS completes. See, I'm gonna run this. See if I get or so I created a node and then I'm gonna submit. Right. Water break. Alright, so we can move to the next problem, I believe. Mm, so this is called maximum width of a binary tree. Okay, so this problem is called maximum width of a binary tree. Let's read it. Given the root of a binary tree, return the maximum width of the tree. The maximum width of a tree is the maximum width among all the levels. The width of one level is defined as the length between the end nodes, the leftmost and the rightmost non-null nodes, where the null nodes between the end nodes that would be present in a complete binary tree extending down to that level are also counted in the length calculation. It is guaranteed that the answer will be in the range of a 32 bits integer. So our input is root 13253 null and 9. Our output is 4. The maximum width exists in the third level when we subtract 9 from 5, so we get 4. So this is the maximum width. If we take these two, the maximum width is 3 minus 2, which is 1, which is not maximum. So definitely it's in the third level. We have this binary tree. So here the difference is 1, here it's 4. Like, well, actually my logic is a little different. Wait, maximum width. Width of one level is defined as length between the end nodes, leftmost and rightmost. Okay. The maximum width exists in the fourth level with length 7 because this is the difference. Okay, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Okay. So what we are doing is we are counting the difference because this is my starting node, this is my ending node. But if we count 1, 2, then here it is 3 and 4. So that is why the length is 4. The maximum width exists in fourth level. It's 1, 2, here we don't have 3, 4, then here 5, 6, and then 7. In this example, the maximum width exists in the second level with length 2. This is 1, this is 2. Okay. So let's write down what all we know. Which level? Let's imagine uh, filling in all the number gaps between the leftmost and rightmost real nodes. As of eight binary tree alpha level, there is a formula for width of a level which is rightmost x minus leftmost index plus 1. We need to return the biggest width across all levels. There is also the concept of index numbering. So if a node has index I, then its left child has index 2 multiplied by its right child has index 2 multiplied by I plus 1. This is exactly how a complete binary tree is stored in an array. So the width any level is last index minus first index plus 1, counting all the words automatically. Now thinking of the brute force idea. If I want to go deeper, then I can use DFS and then drag the maximum, I think, and with each DFS. So for each node, while DFSing, and for such we can use dictionary to map as the key value pairs, where each will be mapped, each value will be mapped to the index. So at each level we can compute this value maximum index minus minimum index plus 1 and track for global maximum. This can work, but it uses extra space to store all analysis before computation. You can also do DFS grid for search level by level. So you can track, carry, node and index in a queue instead of just a node at each level. The formula of width will be the same. This one. last index. Five is first index. Prevent integer overflow. Can also normalize its level by subtracting the first index from all the indices at the related gaps. Scales are numbers is small. So we have something called width of binary tree definition with all the binary tree elements as asked to this function. Right from collections and go equal. So from what I know is the same formula that the width is always going to be last index minus first index plus one width. Or I can say rightmost index minus leftmost index plus one. So rightmost minus leftmost is like not rightmost, but the difference between them. Same logic. One, two, three, and four. There's going to be one, two, three, four, five, six, seven. Count all the null gaps in between. The key trick will be number nodes like a binary tree. So, so it's the same formula this one. If child is this, then index this. Then with DFS is basic. No, so the proof So in the optimal, we can do BFS, gallery, each level, compute with on the flag. So I'm gonna write Q equal to BQ, say root, comma, 0. Why? Why not just root? Node, comma, because I want to track node and index both also. So 0 index root, and I'm gonna assign another variable called result 0. And while I'm gonna track the length of the level size and of Q first index Q 0. This is gonna be the first level index. This level. For an assumption, I'm going to say that last index is 0. And as always, in most of the problems, we do top left, just similar to the last one. So for this image of level underscore size, on the track node, comma, index, right? And now, just I mentioned I want to normalize as well. Normalization is subtracting first index, so indices start at 0 each level. This will basically prevent indices from growing to 2 to the power n on deep trees. But this will prevent overflow. So I'm going to prevent this, write index minus equal to first index and last index equal to index. So here what we are doing is we are final value will be the rightmost index. Then we also know the formula that left child gets 2 multiplied by index value or 2 into I. And then right child gets 2 into index plus 1, right? So I'm gonna write f node dot left q dot append node dot left comma 2 multiplied by index if node dot right then q dot append node dot right comma 2 multiplied by index plus 1. about one-sided normalization to return the result. So basically, most normalized to zero. So now width becomes index minus 0 plus 1. So const. Think here it should be because we are wrapping it as a tuple. So node and index should travel together, right? So root and zero should be together. Should be in line with the for loop and this result. Yes. Because last index isn't like final until every node at the level is processed, right? So every node at the level should be processed first and then the last index should be like final. So let's see if we had to like run an example how would it be. Suppose take this one. So let's see at level one we have node and index mapped together, right? So one then zero. Since last is zero and width is one. Last is basically the leftmost. The leftmost. Sorry. Not the leftmost, the rightmost. Then we go to level 2. What all do we have? Have two nodes 3 comma 0 and then 2 comma 1. Here last is 1, is 2. Because here the last one is 1, but there are two elements, right? So it's just 2. And with this last index minus 0 plus 1. So 1 minus 0 plus 1 is 2. Go to level 3. What all do we have? We have three elements 5 comma 0. Then we have 3 comma 1. Then we have 9 comma 3. Right. And now we'll run it again. So my last becomes 3. This last one ready. Width becomes last index minus 0 plus 1. So 3 minus 0 plus 1 is 4. So it becomes 4, which is my answer. So we return 4. I'm thinking about time complexity. O of n because every node is visited is just once. Comes to space complexity, similar as the previous problem, is Q holds almost one level. So what is the pattern here? So here we are doing BFS plus index encoding. And the trick is whenever a problem involves width or finding the gaps in a binary tree or counting words between real nodes, think about encoding positions using a complete binary tree and using this for left, right, this one left child and right child. This is the formula. That also another thing to remember is always normalize or level, avoid overflow. Let's see, unwanted, submitted. want a trick and then solve the next problem. Okay. Um, okay, so this is the problem. It's a medium problem as well. It's called count good nodes in a binary tree. Let's read the problem statement. Given a binary tree root, a node x in the tree is named good. If the path from root to x in the path from root to x there are no nodes with value greater than x. Return the number of good nodes. Okay. Nodes in blue are good. So if this is our tree, 3, 1, 4, 3, null, 1 and 5. So 3, 1, 4, 3, null, 1 and 5. Our output is 4. How? So explanation. Nodes in blue are good. Root node 3 is always a good node because it's the root node. Then we go to node 4. 3, 4 is the maximum value in the path starting from the root. Okay, so this becomes the maximum, right? Then we move to node 5. Then this becomes the maximum value in the path. If we go 3, 1, 3, then this is the maximum value in the path. So we're gonna only keep track of the maximum values. This is a good node, this is a good node, this is a good node, and this is a good node. So 1, 2, 3, and 4. That is what this will. Another example. 3, 3, null, 4, 2. So we move to node 2. So it is 3, 3, 2. It's not good because 3 is higher than it. Because here we move down, this is higher than this, right? Always, always the bottomest node should be highest. That is why it's a good node. So here 4 is the maximum among these two. So these are our good notes, but not this path. So let me write down earlier was called if no ancestor above it on the path from you has a bigger value. than- So no one in the path should have bigger value than this or this or this. So only last one should be maximum. Then only we can call it a good number. Root by default is always good. Our goal is to all the good nodes. So I think of root force idea. What you can do is go to the bottomest leaf and then walk all the way back up and compare or it will all the way back up to the root, collecting all the ancestors. For all ancestors, we can then check if any ancestor is greater than this node. If none greater, then we count all the good nodes. But here the drawback is it will take us O n square because every node is we walking the whole path. Let's think about the optimal approach. Instead of a node like traveling all the way back up every time, what if we store it somewhere temporarily? What if we store it somewhere temporarily, like making sure? Not sure. So depth first search to go to the depth first search to carry track the next values and so forth in the path. Then go to the current each node if node of value is greater than equal to max of it is a good node. Then we can pass max so far node dot down to already have a definition for good notes mistake. Go back to tree. Okay, let's think about it. So now I'm gonna create another definition. I think. So let me see. I'm gonna use DFS, which will take node and the maximum so far between a path from root to the children. So if there are no nodes, so we are handling the edge cases first. If not node, we return 0. So basically no nodes here equal to 0. Next we can check if the node is good. So let's buffer like already initialized with this dot value is greater than equal to x. So far, if it is greater than if the current value of the node is greater than the maximum value so far, then initialize is good equal to 1, else keep it right. Then we can update max for the path. So I'm gonna say max equal to max of max so far and no value. I'm gonna use function, call it the function. So goes with intermediate, keep the so I'm gonna call left equal to, I'm gonna call this function in DFS node dot underscore max. So I'm looking for right node dot right underscore max. Once this is done, then we can put the number of rows plus the extra row. So root by default is good, right? So we need to factor that into start DFS from root. Root is always good. So start max. Max. Why infinity? Because we know any value is always less than like greater than minus infinity. It's like this. Yeah. So always counts as code. Capital DFS. Because we're counting the root as well. This is supposed to be one layer. Yeah, like this. So it should map. Not here. Parallel to the left. Okay, now let's try to run an example. Let's take this one. Right. So first, I'll call DFS function. And first, I'll pass the root, right? Comma minus n. So this is running. This happens, it's gonna return 3 because 3 is always greater than minus infinity. So it's a good number. It's a good number. By a time is a 3 is a good node, and now I know 3 is a good node, so my new max becomes 3. And so my new max becomes 3. Next, I'm gonna be calling DFS and I'm gonna move to this route left. So 1 comma 3. And if I go and do the operation, I know 1 is not greater than 3, like 1 is less than 3. But we don't want that. We want the one which is down should be greater, right? So it is up. So basically 1 is a bad node. New max stays the same. Now we move on, we call DFS 3 comma 3. Let's see. 3 is greater than or equal to 3. Basically equal to 3, right? 3 is equal to 3. So 3 is a good node. So now I return 1. Next we go to DFS 4 comma 3. Then we do the operation. 4 is greater than equal to 3. So we can say it follows. So 4 is a good node. And then our new max is updated now. So new max becomes 4. Next we go to DFS 1 comma 4. But here 1 is less than or is 1. Here 1 is less than 4. So it does not follow. So 1 is a bad node. Return 0. Then we move to DFS 5 comma 4. Then we realize that 5 is larger than 4. So 5 is a good node. And we return 1. So now we count the total. So total is 1 plus good node plus bad node plus good node plus good node plus bad node plus good node. So it becomes 4. So we return 4. Now let's think about the time complexity. Complexity is O of n. So every node is visited exactly once. Think about space complexity. Complexity is O of h because it's recursion. So recursion, stack depth, height. So what is the pattern here? It's basically carry state down DFS path. Instead of storing entire full ancestor history, what we are doing is reduce it to one number we need, which is max so far. So we are keeping track of max so far instead of reiterating and each node is going all over the path again. So I'm gonna track and ask what is the minimum information I need from all the ancestors, which is max so far, right? So think about, can I compress the entire ancestor history into a single running value passed down DFS? I'm gonna run it now. Put 4, 3, 1, submit. the next problem. Let's read this problem. This is also a medium problem. It says convert binary search tree to a greater tree. So, given the root of a binary search tree, convert it to a greater tree such that every key of the original PST is chained to the original key plus the sum of all greater keys greater than the original key in the BST. As a reminder, a binary search tree is a tree that satisfies these constraints. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of node contains only nodes with keys greater than the node's key. Both left and right subtree must also be BSTs. So you can see this is a binary search tree. So this is the node and this is the key. Then you can see uh, the value of the right subtree is always greater. So 6 is always greater than 4, but 1 is always less than 4. So the left subtree is always less than the node's key. The right subtree is always greater. Similarly, here 7 is greater than 6. 5 is less than 6. So 2 is greater than 1, but 0 is less than 1. So, yeah. So my root input tree is 4, 1, 6, 0, 2, 5, 7, null, 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 3, null, 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 8. So the output should be 30, 36, 21, 36, 35, 26, 58. But if visit here, the node value is 8. 0 plus 8 is 8. Reversely, we can take 7, 6, 5, 4, 3, 2, 1, 0. Okay. Gonna do a walkthrough first, I think. But let's write what it's asking us. For every node, we need to add all the values into the. So if I'm here, so greater than 4 is 5, 6, 7, right? 6 plus 5, 11, plus 7 is 18. 10 plus, okay, not this way. Plus 7 is 15. Plus 6 is 21. 21. Okay. Mm. add that zone to the node zone value. Gonna do a walkthrough. Reverse order here. A binary search tree in order traversal is basically left, then to the left, and then to the right. Case values segment order. So reverse in order, right, left, and then left. Gives ascending order, and then reverse of in order. If you walk okay, reverse in order, keep a running sum. The time we visit and load the running sum and then every greater value. We just need to add and sum to the a brute force idea for every node for traverse traversal. Signing up and add node. But this is hence quite hard because we're visiting every node and doing full traversal again and again. Okay, this will scan every time. Optimal approach. Use reverse in order. So reverse in order would be first we go to right node, go to the left of the so node add the value to the run. So then set dot value equal to next one. Okay, pass. So we have a definition called convert BST, which has three mode and outputs of three as well. Okay, so if I start at 0, 34, then 1, so 1 is greater, but the sum remains same. Then I go to 2, 2 is greater, so I'm going to do 36 minus of 35. Here, then 3 is greater, so I'm going to 1 minus 2, 30. Then I go to 4, 33 minus 3 is 30. I go to 5, 30 minus 4 is 26. Go to 6, 26 minus 5 is 21. I go to 6, 7, 27. 21 minus 6 is 15. 15 minus 7 is. Then I go to 8. 15 minus 6 is 8. Okay, understood. So, running sum at each step. Sum of all values. So here I have self. So I'm gonna first write self dot underscore sum equal to 0. I'm gonna do def reverse in order node. If not node, return. So the visit rights update first. Right one is always greater than the node, right? So 6 is always greater than 4. And the 7 equal to sum of self dot running of sum plus equal to node dot value. So passing the value to the reverse in order function, then updating the running sum. So left subtree, these are all the values smaller than the node. It's add and then we return a root. Let's run an example. So now I'm gonna do reverse. So if I do reverse in order, then reverse I go from right node and left. So rightmost is 8, right? So 8. Then to 8 the node is 7. Then 6, 5, 4, 3, 2, 1, 0. Now I know my sum is 8. Running sum. And then do node 8, node of sum dot value is 8. Next, I move to 7. And at 7, my sum is 15. Node 7 dot value is 15. Sum becomes 21. So you can see the pattern here. First it's 8, then 8 plus 7 becomes 15. 15 plus 6, 21. 21 plus 5, 26. 26 plus 4, 30. 30 plus 4, 30 plus 3 would be 33, right? So my final output becomes following this 4160. So I'm gonna write it that way. At 4 we have the sum is 45. At 1 we have the 36. Then at 6 we have 21. Then 36, 35, 26, 15. And then similarly for all others. So here complexity is of n. I think this is gonna be my last problem and then I'll take a break. Resume maybe in the evening. So what is the pattern here? This is reverse in order BFP. So whenever a problem needs values descend order from a BST with the reverse. So basically comes this. running soundtrack is you never recollect all the values. There is self as well. Just smartest. That okay, last problem for the day. I'm done for today. I'm exhausted, so not exhausted, but I'll resume back